Good afternoon, everyone. I'm going to continue with another apparent weight type question. This one becomes a little more difficult as we also have some kinematics involved with this. This question is revolving around the idea of a crane lifting loads up onto a building or from on top of a building down to the ground. And engineers constantly have to think of what type of load the crane can withstand. There are safety mechanisms involved in case if things aren't working correctly. And so there's lots of physics involved, and really they're talking about apparent weight because the loads are moving up and down. So in this particular problem, we have a crane that has a rating for a maximum load of 2,000 kilograms. So we got a mass of our load, and you can see that I've got a box there already. There's a safety mechanism that engages a brake if the load begins falling at 10 meters per second. So in other words, if for some reason this thing is going down and it's going down too fast, an automatic brake engages to try to make it come to a stop. It says if the system needs to stop the falling load within 5 meters. So in other words, the moment it detects that it's going 10 meters per second, it needs to make it come to a stop within 5 meters. What tension must the cable withstand? So the cable obviously needs to pull up at that point, and it's got to be stronger than just the force of gravity because we are also making it come to a stop. So there is a lot of kinematics here. I'm going to include some information with this. We're going to include the ground. So if the ground is, let's say, over here, then that means that this distance here is going to be 5 meters. Oop, come on. I don't know where that W is coming from. All right, 5 meters, there we go. So that's a piece of kinematic information that we have, and the starting point is here and the ending point is here, so this 5 meters is going down. We also happen to have that up at the top here, the initial velocity is equal to 10 meters per second. Okay, and again, this 10 meters per second is going down. And then at the end, down at the bottom over here, we have the final velocity is equal to 0. So when we're looking at this particular problem, we have kinematic information, but we need to move over to a dynamic situation. We need to figure out dynamics. And the link between those two concepts is acceleration, because that's what exists in both kinematics and dynamics. So if we're able to determine what in this situation the acceleration would be to create this to work, then I can move over to dynamics, F equals ma, and figure out forces. So that's the work that we're going to have to do first, is we're going to have to figure out what the acceleration is in this particular scenario, so that way we can move over to dynamics. At this point, this object is not in free fall. If I draw a free body diagram for this, I know that I've got the force of gravity on here. Let's see if I can change. Can I change the color? Maybe not. I know that this is force of gravity. Oh. That's what this particular force is. And then I also have a tension going up. Oh, that's not what I want. I have a tension going up. And hopefully you can see that this tension is larger than the force of gravity. So this is a force of tension. There we go. Okay, so what we're going to use is we're going to use kinematic equation 5 to figure out what the acceleration is, seeing as we have the ending velocity of 0, we have the starting velocity of 10, and we have the distance here of 5. Now before we put in our values, we need to make sure that we understand what we want positive and what we want negative. It's going to make sense that the acceleration is going to be up. If it was down, then that just means that this 10 meters per second is going to get faster and faster. So most of the time, students prefer down being negative and up being positive. And so if we put in this 10 as a negative, this 5 as a negative, then hopefully we get an acceleration that's going to be positive, meaning up. And I think that's what most of you are going to prefer. So even though inside the information that I have, the 5 and 10, we're going to make this a negative 5 in the equation and this a negative 10 in the equation. So now I can place in my values here. So I know that the ending velocity here was 0. I know that the starting velocity here my starting velocity here was negative 10, bracket negative 10, there we go, and we square that, and that our distance here was negative 5. There we go. So we'll do the math that we can. The 2 times negative 5 is going to give us a negative 10. Negative 10, and we still have the a. And we know that negative 10 squared, is going to give us positive 100. So we'll move the 100 to the other side. Where we are going to get negative 100 equals negative 10a, and we're going to get that the acceleration acceleration is going to equal negative 100 divided by negative 10 to give us a value of 10 meters per second squared. There we go. So now we've got the acceleration of this particular box when it's falling and all of a sudden the tension pulling up on it. It's going to accelerate at 10 meters per second squared. We got a positive value indicating up, so that makes sense. So now what we need to do is we need to think of our dynamics. Okay, so I've got our two equations for F net. F net equals ma, and F net equals all the forces combined. I'm just going to try to make myself a little bit more space here. I'm going to kind of make that all a little bit smaller and move it up over here, and that's going to hopefully allow me to have a little bit more room here. There we go. Okay, so I'm going to try to introduce an idea here that sometimes might be helpful, maybe not exactly for this question, but for some other questions that you might come across. I'm going to focus on this equation here first and develop it based upon our dynamics here of force of tension and the force of gravity. So let's go into this, and we'll make this equation based upon this particular scenario. And the two forces that I have in this particular case is going to be the force of tension and also the force of gravity. Let me get rid of all these dots. But one thing that I have to keep in mind here is that the force of gravity is going down and the force of tension is going up. So one of these needs to be positive and one of these needs to be negative. And in our kinematics, we had already said that down was going to be negative and up was going to be positive. So since the force of gravity is pointing down, I am going to make that one the negative. All right. Now ultimately the question is going to be asking us to find what this value for the force of tension is, which means these are the other two that I'm going to need. But rather than finding these values off on the side, I'm going to replace what these things are. Oops, sorry. The F net equals MA. I'm going to put that in there. I also know that FG is equal to MG. So here I've got that FG is also equal to MG. So I'm going to change this equation now where I'm going to place in those particular ideas into the equation. So in other words, I'm going to replace that F net is now mass times acceleration. And I'm going to replace that Fg is mass times gravity. And that's called a substitution. And so now at this point, what I can do is I can fill in my values. I know what the mass is, it's 2,000, and this mass and that mass are the same. I have the acceleration from over here, 10 meters per second squared, and I know that gravity near Earth's surface is 9.8. So I have all of these values, which means that now it's just algebra and for me to figure out the force of tension. So let's go ahead and do that. So let's put in MA first. We have a mass of 2,000. We have an acceleration of 10. And then over here, we have a mass of 2,000. And we have gravity at 9.8. Okay, and now we can do the math that we can. 2,000 times 10 gives us 20,000. And 2,000 times 9.8 gives us 19,600. All right. So remember what this really means is that in this particular situation, the force of gravity, that's what this term came from, is 19,600. So this value, this force right here, is 19,600. And the net force causing this acceleration is 20,000. So that means that this force here needs to be 20,000 newtons more than this force here. So hopefully you can see already that mathematically I'm going to add this over to the other side. So we'll get then, and I have to erase most of this, that the force of tension is going to equal 20,000 plus 19,600. And of course that's going to give us 39,600 newtons. And so that's how strong the cable needs to be. It is clearly needing to be much, much stronger than just what the weight of the load is. Its apparent weight is much, much higher because you're having to accelerate it up. So we get this value here, and this is our final answer. All right, so this kind of style of question is going to be on the next couple of items that I'm assigning. And as you start working on some of the questions, doing this idea here where I substituted this in is a good habit to start getting into, because sometimes there are questions where this is the only way you can move forward. It's that you can't find FNet just on the side or FG on the side to try to figure it out. You have to substitute those in, and then from here you can do some extra mathematical work. All right, we'll talk to you guys soon. Bye.